Welcome everyone to our online research seminar. My name is David Lamb. I'm the Chief Scientist of Food Agility CRC and I'll be your MC. Just before we introduce our speaker, just a little bit of background. For those of you that are unfamiliar with the Food Agility Cooperative Research Centre, we are a CRC dedicated to unlocking the power of digital to transform our agri-food sector. Whilst we aren't the only CRC concerned with agri-foods, in fact there are 6, and indeed we have formed ourselves into a consortia of agri-food CRCs in Australia. Food Agility, we are specifically dedicated to the power and role of digital in that transformation process. The aim of this seminar series, which we hope will be a regular event on our virtual calendar with you, is to bring to life some of the amazing talent and activities we have in our research community. Consider this like a departmental research colloquia, albeit with a department that encapsulates more than 8 university partners and 3 state agencies. In fact, across our partnership base and in terms of our research capacity, we've more than 300 researchers who work in areas specifically related to our capability pillars. That is around the data sources and the sensing technology, the data analytics, and the sustainable food systems that enshroud them all. And in fact, across our partner research organisations, we have more than 12,000 researchers whom we believe are working in allied areas, and together we can bring significant domain and contextual experience and knowledge to bear on some of the gnarly problems and challenges and exciting opportunities of our agri-foods time. Now, you are all part of that community, either because you're partners of our research organisations or you're part of the industry that seeks to have problems solved and who will be the ultimate beneficiaries of what we're doing. And I'm delighted to see that in our attendee list, we have a substantial membership participation rate of frontline researchers. And that's the whole purpose of this research seminar series. So before I introduce our speaker, just want to cover off on some housekeeping. First of all, this session is being recorded. We'd like to make this session available to you and your peers, colleagues who can't attend after the event. So please note that we are recording as we proceed. We certainly welcome your questions as Richard, our presenter, is progressing. Unfortunately, we can't accept your questions verbally because we don't have that facility in the system. However, if you could use the Q&A tab at the bottom of the screen and put your questions up, as the MC at the end of the presentation, I'll come through and communicate those questions to Richard to hopefully answer. If we have more questions than time allows, then I'll cherry pick a couple of the representative ones, but we certainly invite you to follow up directly with Richard, our presenter, after the event. Now to our speaker. The topic of today's research presentation is, well, artificial intelligence for agricultural intelligence, AI for RAI, as Richard puts it. And it's a privilege to welcome our guest, Associate Professor Richard Zhu. Data on and of its own is nothing. If it's to make a difference in our agri-foods lives, data, information and experience forms a closed loop. Artificial intelligence and machine learning are the cogs and wheels that enliven that loop. An old farmer mentor friend of mine used to always say that when it comes to farming, artificial intelligence is no substitute for natural stupidity. And I guess to him what it means is about the lessons learned, often the hard way. That's what makes him a better farmer. So it's great to see when I read Richard's biography and presentation synopsis that in addition to the basic machine learning paradigms of supervised and unsupervised learning, we've also got the notion of reinforced learning, basically algorithms and processes that learn from experience. So in his language, and in the language of my farmer mentor friend, we envisage that artificial stupidity will be an awesome friend, if not substitute, to natural stupidity. Professor Richard Zhu has an impressive record of AI and machine learning innovation, and an equally, if not more impressive, global following of his work. Richard is an associate professor in machine learning at the University of Technology Sydney, one of our core foundational partner universities in the CRC. He leads a team of 30 people, including postdoctoral researchers, PhD students, our capability of the future, of course, and data engineers. Richard and his team have worked with banks, in e-commerce, with government, utilities, defence and law firms. Richard's established the Deep Learning Sydney Meetup, which is more than 4,500 members. And of course, artificial intelligence machine learning has found its way into many agricultural applications. And this is where AI for AI comes in. So it's with great pleasure that I introduce Associate Professor Richard Zhu to our virtual podium to tell us more about AI for AI. Welcome, Richard.
All right. Thank you so much, Dave, for the invitation. And it's such an honor to be able to give that particular talk. And it's also a pleasure virtually meeting everybody. So I'm just gonna get myself started. So yeah, like what Dave was saying, that the talk of today is AI for AI, artificial intelligence for agricultural intelligence. So David has already had introduced who I am, so I'm probably not gonna repeat that. I'm just gonna. So yeah, the first section of this talk is what is AI, machine learning, and also deep learning. Probably you have heard these couple of buzzwords quite often these days. So let me try to do a bit of demystifying for you before we sort of talk about how AI is actually applied to agricultural settings. So AI is everywhere, right? So when you get up in the morning, you probably are using the facial recognition to unlock your phone. You probably will ask Siri what your daily routines are going to be. That's powered by AI. You will use the Google navigation or any other navigation tool. So the routing algorithm is actually done by AI. Then when you go check your emails, the spam filtering algorithm, that's part of machine learning and it's AI. If you wanted to actually send an email to your client and you want to impress them by sending that email in their mother tongue language, that automated translation, that's powered by AI. Now, if you're going to, choose Zomato and choosing, what's the restaurant to go to, and that's the recommendation system is part of AI algorithm. And then, of course, if you pay for your bill using your credit card, there's a bit of an algorithm that goes in the back end that actually checks for financial, security, and that's AI. And of course, not very long in the future, if you got drunk and you want to go home, your self-autonomous car is going to drive you home. That obviously will be powered by AI. So I don't know how long it's going to take, but I wish that we will see autonomous cars running around within the next decade. So AI can actually be used in lots and lots of areas, and these are just some of the examples of the applications that my talented students and postdocs and engineers and and people in my lab has been working on. But they certainly do not represent the all AI applications, and we will certainly engaging into more of applying AI to the agriculture settings in the future as well. All right, so a very, very quick history of AI. So to get the machine to do part of human thinking has always been the dream of mankind, even since the Bronze Age. And with the invention of the computers, that kind of dream will become a reality. So in the 1980s to about 2008, there's a lot of talks and a lot of hypes around that area. And we can't call them AI winter because people start to think computers get so much better, and hence artificial intelligence is going to take off. But no, it didn't really take off. And until about 2008, there was a fairly significant event in the world of AI. This is where Stanford University has released its data set. It's called the Imagenet Challenge. and it contains 3 million images with about 3,000 classes, and each class obviously have 1,000 images. And so they started this particular, challenge, and that challenge has ended in year 2017. And the reason why it got ended is because, the recognition rates from some of the winning competition, algorithms became so much better. They even became better than human recognition in terms of the accuracy. So there's no need to actually run that particular challenge. It's no longer challenging enough. And also people probably have heard about things like AlphaGo, which is an algorithm that's made by a company called Google DeepMind. And it's using it to beat the best Go player in the world. Now you can do that with chess relatively easily by exhaustively search all the movements. But game of Go, the amount of movements, it's just impossible to exhaustively search by the computer. You have to actually get a computer smart enough in order to actually play it without exhaustive research. So yeah, all right. So what kind of fueled the growth of AI? Obviously the data. Now data becomes a lot bigger and they'll become a lot more accessible. And also the algorithms has become so much better. And one of the reasons why the algorithm became so much better is because there are so many people, so many smart people started working on it. I think there's a lot of people come from the academia world attending today's talk. So I think some of you probably publish papers into a venue called archive. So this is designed to get people to publish their work before it was sent to the peer-to-peer review journals, or whilst waiting for peer-to-peer review journal results. They publish them into a archive. So I did a search on archive, and I found out there's about 100 papers related to the area of machine learning that's been submitted to that archive every single day. So you are looking at least 30,000 something papers in that field to be submitted. That's 30,000 new algorithms to be invented every single year. That's actually a phenomenal number of research that's happening. And another important factor is the wide usage of GPUs, which stands for graphical processing unit. I'm sure that a lot of you guys play games. You know that graphical processing unit was initially designed so that your computer can render the graphics a lot better. Now, obviously, people start to take advantage of that, especially the deep learning. People start taking advantage of that because solving some of the deep learning algorithms is, in fact, has very similar characteristics of rendering the graphics in your machine, because both of them can be done in parallel, and the arithmetic is relatively simple. So, people sort of say, why don't we take advantage of the existing GPU structure and we get it to actually train our artificial intelligence models. So these three factors has actually made, the rapid growth of the artificial intelligence algorithms. And here you go, some of the buzzwords. You probably have heard this words AI, machine learning, and deep learning all the time, but how are they going to be related? Now, AI is everything, right? It's every bit of technology that actually allows it to kind of participate or help to do a bit of human thinking. That's AI. And machine learning specifically to do with a set of algorithms that's driven by mathematics and statistics that looks at the patterns of the previous seen data. And the algorithm will then extract the patterns automatically from this previous seen data and apply them into the future unseen data. So deep learning is actually a part of machine learning. Hence, it's actually part of artificial intelligence. And it does whatever machine learning is set out to do, except in deep learning, you are using neural networks. In fact, lots of layers of neural networks. All right, so yeah, here's the three buzzwords for you. Now the question is that, it's actually quite interesting, especially in the last few years, that deep learning now became the dominant workhorse of artificial intelligence. So a lot of people start to equating deep learning with AI, but that's not entirely correct. But however, it does actually, it's proven that a lot of the useful algorithms is actually deep learning driven. Cool. So I'm just going to show you very quickly about what deep learning does. So I'm going to show you two seminal research in that area. So one is called convolution neural networks. So what convolution neural network does is that you have, so just imagine that you wanted to perform a facial recognition. Now, facial recognition is a classification problem that you have lots of training data from each of the person, and you try to train your algorithm to recognize if you have a new photo, should that person be Sarah or John? Now, it turns out that if you're using the photo as it is, i.e. it's an original representation, the recognition rates is pretty low. However, using neural networks, by extracting the relevant features at every single layer, the recognition rates is actually going to be a lot higher if you actually been using the neural representation of your original image, right? So what neural networks, or in this particular case, convolution neural network does is that it simply has been useful to transform your data from your original representation into a new neuron representation that turns out to be a lot more robust to carry out a lot of the functions that your algorithm is designed to do. Here's another, seminal research in machine learning, in deep learning. It's called recurrent neural networks. This, in that particular example, it's called, neural translation. So what that does, that is, it translates a sentence from one language to another, right? So in this case, Chinese is being feeding into an encoder. And out goes the decoder. You are translating the English. Now that's one of the challenge of translation is that the words. If you look at that particular word, and this word is actually depending on every single word in your encoder, as well as all the preceding words of your decoder. Yeah, that's how human translate stuff. Now that's, but how much of a contribution this particular word will get from each of these words in the encoder. This will be, determined by the computer. By the RNN algorithm specifically. Now, if you look at this particular diagram here, you probably see some of the weighted lines. The heavier the line, the thicker the line, it means that more contribution that particular word will get from the, from the words in the encoder. The lighter it is, the less of the contribution. And now that particular, contribution has a name. It's called the attention, right? So by the way, this particular algorithm is called sequence to sequence with attention. Very intuitive, algorithm name. And that's actually came from Google. Now, if you start to wonder why since 2016, the Google translation become a lot more accurate is because of that particular algorithm. So in 2016, Google has now used neural, sequence to sequence with attention to do majority of its translation. All right, so with that said, I'm going to show you some of the applications of, machine learning, of what machine learning can do. And these are the applications not specifically related to agriculture, but hopefully it's going to give you some ideas how they may be applied to agriculture area. And I'm also going to show you some of the things that we have done in that space as well. So this is a work come from Stanford about 4 years ago. So what that does is that it does automated image tagging. So what I mean by this is that you supply the computer with one image or photo, and the computer or the algorithm is able to segment the important elements out of that image automatically. Then it will attach a natural language to be associated with every single image parts. Yeah, so it's called an automated image, tagging. So you basically supply an image, the computer will actually write natural language, for it. And one of my PhD students' work is the reverse. The input is actually a natural language, and the output is what the computer is trying to guess what might be the best image to depicting that particular sentence. So that's very cool. As you can see, that the image that we have generated doesn't look, extraordinarily real, but that's that's a start. And I also think that a good research topic is a topic that the student can never finish during the 3.5 years of candidature. But along the way, the student will be able to generate a lot of interesting results. In NLP area, NLP stands for natural language processing. By the way, we will actually talk about that a lot, in the rest of the talks. So Washington Post robot actually start to publishing, news articles. So we have actually done something very similar work with New South Wales government, specifically looking into using NLP technologies to aligning the job advertisements with the vocational education training sector. We have companies like Salesforce, they also have began this research on how to translating natural language to SQL. For those of you who are not familiar, SQL is the language that people use to access a database. And that's a very mundane job to actually write SQL queries. So people thought, why don't we actually just, translate natural language to database queries so that literally anyone could actually access a database without actually knowing the technical details. So we also did something like that before, a very similar kind of research where we have built the NLP to SQL queries, specifically to do with the transport data. Actually, we do have our demo sites where we actually showcase some of this research, and you can actually play around with it. I will actually share with you at the end of the talk as well. So this is what Sony has done. They wrote a robot that actually be able to create a music by itself. I think if I play it, not sure if anyway, I'll stop that. So Google did the same thing of actually getting the robot to essentially writing its own song. We have done something kind of similar. If we take the left-hand play of the piano, so that's the input, and we get it to, sorry, I actually played the wrong one. This is the input. If we actually take only the left-hand play from someone playing piano. And then we try to use that to guess what happens if two hands are playing at the same time. Cool. All right. So also we have done, and also, there's a lot of work have been carried out in the computer vision area where IBM Watson has actually produced a trailer entirely made by the machine, using deep learning technologies. And the way they did it is that they have trained 100 horror films. And so the machine can know how to actually produce a trailer of a horror film. We've obviously done a lot of work in that area as well. We have built a automated boat and car counting algorithm that goes around the coast of New South Wales, count how many cars and boats in there. And then we did a lot of work on the sports area as well to pick up people's gestures and things like that. So this is a very cool research that's happening. Remember I said about the AlphaGo have beat the best Go player in the world, and that's powered by a particular algorithm called reinforcement learning, which I'm going to talk about that a little bit as well. Now, having beating the Go, they have also now have this called AlphaStar, that actually start to build beating the best StarCraft player. So we have actually done some stuff in this area as well. Obviously, we don't have the similar kind of computing resources, comparing with DeepMind. So we can only participating in a fairly sort of minor, competition where it's actually doesn't require heavy computation resources. So that particular challenge that we have joined, it's the IEEE Games Conference on micro RTS. So it's a very simplified version of the real-time strategy game. And this is what my postdoc have done. So this is the win rates for UTS. Our bot UTS IMS has actually beating by other teams by a very, very large margin. So, I guess for people who are in that AI professions, the good news, the job prospect is pretty good. So these are the couple of articles I found in the sort of in recent times. There's also talk about AI skill shortage. So it's actually good. All right, so I'm saving the best for the last. I'm going to talk about AI applications in agriculture area. So these are the very common examples. So whenever I talk to people about AI in agriculture, these three things has almost always been raised. Drone for precision irrigation, using image processing to detect disease in plants and counting sheep and cows and that kind of stuff. And also here's a funny, interesting example where Japanese farmers, it's actually been quite a couple of years now. I think I first saw it in 2016, where Japanese farmers have using convolution neural networks, the one that I've shown you earlier. They use it to actually sow cucumbers. I did not actually realize that there are that many types of cucumbers, until I saw that article. So that was very, very interesting. But however, AI can do so much more. So here's a collection of things that I actually have, found, and I am sure that some of these technologies either has already been applied, or they will be applied to agriculture very, very soon. So, firstly, this is a work on GAN. So GAN stands for Generative Adversarial Networks. So let me very quickly explain to you what GAN does. So just imagine that you want to get the machine to automatically, creating a new Picasso drawing. You will need to give the machine a lot of examples of previous Picasso drawings. So in the machine, it has got what we call a generator that's going to generate fake Picasso drawings. And at the same time, you have a discriminator that actually can detect the fake one from the real one. Yeah. So therefore, the two algorithms will need to compete with each other. Hence the name adversarial networks. So initially, the generator doesn't actually know how to generate realistic looking images, and the discriminator doesn't even know how to distinguish between, like a fake or real, but they were competing with each other. So towards the end of the training, i.e. when the algorithm converges, the generator and discriminator, they both become super, super good in what they do. And therefore, you're actually going to get yourself a really great generator to be able to generate very realistic, images. So you might wonder, how does that going to do with, AI in agriculture? There's lots of things that you can do with it. So, here is an example where, people can just start to think about, so what happens if I want to grafting, for the two fruits together? And this is where people can just selecting any kind of, pairs of, fruits, and they can get a GAN to actually generate the results, to look at the, the textures and stuff before even planting it. And also, there's a version of GAN, it's called the conditional GAN. So you can actually get it to generate Picasso images by actually putting in a little bit of condition to it. So you probably wanted to say, I want to generate an image of a man, right? Or wearing red clothes and that kind of stuff. So you can apply them to, agricultural settings as well, where you can actually supply with the image of the banana to begin with. And you can actually specify the conditions to say, store in a warehouse room temperature for 5 days. And then you get the generator to generate what it might look like, after it's been storing in that particular condition. Now, I'm kind of using image as an example, but it doesn't have to be, right? These can just be a bunch of attributes, right? So the texture, the size, the weights, how rotten it's going to be. I'm using images just to, visually, looks a bit nicer. Of course, then by changing the conditions to another one, the generation results is going to look very, very different. So in generative adversarial networks, a lot of cases, some of the new research is also specifying what you don't like to generate. So that's what we call negative examples, and we can use the similar kind of paradigm in the agriculture as well. So you can by supplying the results that you don't actually want to get. So then, therefore, you will be able to generate. You can make the generation a lot more controllable. So here's the work we have done for transport, in which we have worked out what is the best time to schedule the replacement buses when the train's on maintenance. So here's just a little example. And in order to do that, we framed this into an constraint optimization problem. So the idea, the things that we want to achieve is to minimize the average waiting times for everyone. But the constraints we're going to take into consideration is the maximum number of bus routes, deployment rates, and number of buses can go through a particular day, and how many bus bays in the station and things like that. Now, the same thing could actually apply to a particular, to maximize the profitabilities of a particular farm. So obviously that's the goal, right? To make money. But you also have lots of constraints. You need to take consideration of maximum allowable agriculture area, minimum natural light utilities, minimum good transfer times, and other requirements and regulations as well, and also some of the soft constraints, which is also very, very important. So as I promised, we're going to talk about natural language processing. So in our NLP, let me very quickly say that there are three sort of pinnacle research that people, including ourselves, people in my lab are also doing. And one is called translation. Translation, essentially, you're translating from one language to another. That's kind of illustrative. The next one is text summarization. So it's very similar to translation, except that it's not translating between languages. You actually get a very long document, right? And you will actually get a summary out of it. The machine will actually be able to get a summary out of it for you. So in the future, you don't have to read a lot of long essays. You can actually just read a summary extract of that particular essay. And the hardest part of them all is called Q&A, so question and answer. So question and answer is very similar to machine translation, except you have an input, which is in the form of question, and the output is in the form of an answer. And in addition to the question and answer, you also have something called the context. So the machine will need to figure out in the context what are the relevant bits that relates to the question, and then paraphrase them into an answer. And if we researchers crack that particular, question problem, and I think the world will change completely. And we're kind of heading towards that way as well. So yeah, I mean, this is a couple of research that happens in our area where, by the way, this is wrong. So this is, so that's the work that actually done by my student where you're translating the natural language to an image. Apologize, I actually put them in a different order. I just realized. So this supposed to be translating that image, and this supposed to be translating that image. And as you can see that it looks like that, right, from a distance. But, obviously, the photos that we generate still not very, photorealistic at the moment. So here's a very similar research that my student has done. They translate from natural language to a human animation. By the way, we have created a data set for this as well in my lab. And so this type of work is called a sequence to sequence. So we've done we have done sequence to natural language. We've done sequence to image animation. So the question is, can we do sequence to for agriculture? Now, there's something that's very big in agriculture. It's called natural sequencing farming. And we thought, by using this sequence to sequence modeling techniques, it may be in the future that we can actually work out what is the best strategy to actually carry it out for natural sequence farming, and we can actually get generate the guidance for more kind of scientific farming methods by looking at the which part of farm needs to be reserved and which part of farm needs to be inserting barriers and that kind of stuff. And also using natural language processing, potentially we can actually get to write product descriptions automatically by taking a snapshot of a photo of a fruit, and the product descriptions can be generated automatically. Especially after the COVID-19, there's surge in purchasing things online. So giving farmers this capacity, be able to write some, accurate descriptions of their products automatically, that's going to be a very interesting, area to explore. And also we thought sometimes the demand, especially for producers from the farm, can also be automated, extracted by using natural language processing, by getting them to reading newspaper articles. For example, when you start, getting these headlines or, these contents from various part of news sources, and then you'll be able to generate a report that kind of, has a better description of what the market is going to be like. So you can see this is using a combination of Q&A as well as the summarization technologies. So lastly, I promise I'll finish very soon. I'll promise I'll finish on time. So lastly, I'm going to show you the reinforcement learning. So I'm just going to show you one example of reinforcement learning to illustrate what that means, what's the advantage of that. So here is, the first version of Google DeepMind's breakout game. As you can see that, it gets the machine to actually play this particular game and for it to, essentially win the game. You can see that during initial training, it's not as good, but after, it's been training with that many iterations, it can actually figure out movements that's pretty much intuitive to even human. I will get you to watch what happens at the 600 iterations. At that particular iteration, it can even do things like, hitting the brick, like this kind of movement, which I bet a lot of the experienced, a breakout player would not even be figured out. So, see, it's actually excellent. But the things that I really wanted to actually ask you is this. Now, imagine this is the input, right? This is the input. Imagine your brick is here. What is the best movement for you? So if you move left, there's no guarantee you're going to win the game. If you move to the right, there's no guarantee you're going to win the game, right? So there is no instructional label, i.e., we can't actually tell, given that particular scenario, what is the best way or what's the best action to take. So this actually phenomenon has occurred in many areas. So, a potential research project that we are actually, formulating with food agility is to apply them to mastitis treatment. Another example that we actually think about, is just looking at where do you apply, where do you apply for treatments for, your fruits, because, in the one particular state, there is potentially no best solution for that. So you don't know how good that particular treatment is until many months later. So you can't actually figure out what is the best action to take. You only can measure how good that action by looking into something what we call the average total reward you're gonna get from taking that action until, finishing the entire game. So if you've got problems like that, then reinforcement learning may potentially give you the solution, because that precisely is helping, the robot to win the game, and, to help the, cars to drive autonomously, to help the helicopter to actually fly, not falling down, and also hopefully will help the agricultural, to help farmers to actually work out what is the best policy to take. That's actually going to give you the maximum long-term benefit. So yeah, that was the end of my talk for today. I think I'm right on time.
Thank you, Richard. And thank you everyone for your questions, both through the Q&A tab, but also through the number of texts and messages I've received. So I'm going to, if I may, communicate some questions to Richard. If you do have questions and you thought, wow, maybe I should ask them now, please put them up on the Q&A tab and I'll retail them across. So Richard, first of all, just fire some text, and I was getting a lot of side questions around skills, expertise and knowledge. I mean, so depending on how we look at it, so for example, if we put ourselves in the shoes of someone in the agri-food value chain, farmers, processors, whatever, what level of understanding do these participants need to have from AI in order to benefit from it, do you think, in your experience?
Yeah, I think, a lot of in the, a lot of people kind of associating artificial intelligence with, say, rocket science and that kind of stuff. I can guarantee you it's not. I mean, artificial intelligence algorithms are a lot more accessible to pretty much everyone than, like 30 years ago. 30 years ago, it's only, this is former technology, is only accessible to people, I guess, within the universities and researchers and scientists and so on and so forth. Nowadays, thanks for the open packages and frameworks like TensorFlow, PyTorch, any people with a competent level of IT is able to play around with AI technologies. And there's a lot of GUI, drag and drop type of applications where anyone be able to use a computer is able to actually experience building their own AI algorithm. So what I'm trying to say is that the accessibilities of AI is a lot higher, tremendously higher than the past. So in terms of people who are in the agricultural industry, having a general understanding of AI, it's always going to be good. And also, just care to say that there's a lot of avenues to actually acquire that general knowledge. There's a lot of blogs, there's a lot of short courses, there's a lot of micro credentials. There's a lot of people who just love to disseminate knowledge. So it's no longer you have to actually read a book of 1,000 pages. You can now just go online and type in a search in YouTube. You'll be able to find out 50 people try to tell you in a very simplistic form of what AI is about, or a particular technology in AI is all about.
Thank you, Richard. So just to follow that thread, because that was another question I received from an audience member, was as a researcher who may not have a background in the analytics and the AI, but wants to bring it to bear. You mentioned, there are effectively click and drag and drop modules or that sort of level of ways of connecting to that capability. So from a researcher perspective, for example, have you got some sites or pointers you could give the audience around if they wanted to look and explore to have a crack at using it firsthand, what they could maybe go about doing?
Right. So, there are, so I can't remember off the top of my head of the actual, drag and drop type of applications, but you can actually do a Google search. It will return you with many. But for people who actually have some programming experience, I highly recommend to learn about Python. So Python is a programming language that people universally use for in that data science, artificial intelligence, machine learning community, and to learn about Python, and at the same time to learn about some of the AI specific packages that's written in Python. So namely TensorFlow, PyTorch, and if you just type those words in, and you can return with essentially zillions of tutorials around that particular topic. Now, I just care to say that programming these days is a lot easier than programming in the, say, 20 years ago, because anything that you like to have some idea of, you type your idea on Google search, the chances that you can find very similar code that other people have written. So yeah, I mean, in summary, I don't know the drag and drop packages off the back of my mind, like off the top of my head, but you can search. But if you actually want to if you do have some IT experience or programming experience, go search TensorFlow and PyTorch, and it's actually a really good tool to play around with. And you'll be surprised how many lines of code you have to write in order to get some very sophisticated things going. It's actually not that many lines of code.
Awesome, thank you. And thank you, everyone. The questions are now coming thick and fast. Richard, I'll read this one to you, if I may.
Sure.
A critical component of many digital interventions in agriculture is trust. So where AI can generate highly specific and precise recommendations for management, for example, how can we ensure that users of the information feel comfortable implementing those recommendations? So this is really looking at that sort of black box type of machine learning. How do we bring engender trust and confidence in the process?
Yeah, I think this is not just specific to agriculture. I think it's actually applies to many industries. Like how much should you trust the machine versus experience? I guess in the literatures of, say, or in the scientific world, we do have a specific matrix for something like that. What we do is that we have, when we have the data, we have the label data, and we split the data into two parts. We got the training and testing. We build this algorithm pretending we do not know the actual label for the testing, and then we verify that particular algorithms on the testing. And also there are lots of mathematicians actually work out the formal proof to essentially see something called generalization bound, is just to see how capable your algorithm is in handling certain error rates or from your data set. But the human trust, that's actually much beyond my this particular talk. How do you build the human trust? It's almost like that's a combination of technical as well as the cultural sort of question from my view. So
thank you, Richard. I'll just go screening down the ever-growing list of questions for you.
Right.
Do you have any experience or sense of the potential biases that can come into algorithms used and applied for agricultural purposes, intended or unintended? I guess unintended in a way.
Yeah, I mean, machine learning algorithms, the bias, the algorithm bias, that is always going to be an issue. Let me give an example. So people have done an experiment where they have started training images of dog's image, but also the images are taken at night. And they also trained all the cat's image that's taken in the daylight. And then they're putting in one cat image at nighttime, it's being recognized as a dog. So therefore, the machine, a lot of what we call the supervised learning methods, the machine just blindly trusting the labels that people have actually done for the machine. So hence, there's a lot of bias can potentially be introduced into those type of algorithms. Now, I think the machine can do so much to sort of reduce the bias. And also, it's actually a lot to do with the data quality and all the rest of it. So again, it's a question kind of, it's fairly open for discussion as well.
Thank you, Richard. I've received a couple of queries about accessing the recording of this presentation and the interaction. So basically, We'll upload this on YouTube in the next day or two, and then you'll receive a notification through your Eventbrite link. So I hope that answers questions. Thank you, Rajwinder, and others for that question. A question, if I may, around the notion of what we're training things to do. For example, accuracy, absolute accuracy and human accuracy, or expectation-based accuracy, are often two different things. How do we reconcile the fact that a system designed for responding to the needs of one user may not suit another, yet ostensibly they're aiming to do the same thing? For example, aid a decision around some sort of management in a farming situation. How do you deal with an algorithm that's been effectively created using one set of data and you want to apply it to something else, and ultimately the end users are different people and may have totally different expectations?
Yeah, I don't. Well, I guess I'm not completely understood that particular question, but I'll be attempting to give you an answer anyway. So I think what you were asking is that how can you design one set of algorithms that kind of satisfy everyone's need? I think that actually has got a lot to do with, I guess, the designer of that algorithm, in the first place. So, again, I might not be answering the question in the right way, or I might not be answering the right question, but let me just share some of my experiences with the audience regarding the life cycle of a data science project in general. So when you engage with a particular industry partner, people will have a different expectation. Now, the problem that Dave was saying, that even within the same organization, the expectation is different to what your algorithm is supposed to do. And the algorithm will actually output a specific outputs based on, I guess, the initial discussion. But along the way, when you start presenting the results, people then will either to say, that's exactly what I want, or other people say, the results probably will portray this picture, but it doesn't actually do that. So I think, at least from my experience, at least, this is much more of a communication problem rather than the technical problems. The way we kind of solve the discrepancy expectation is always have an iterative discussions with the industry partner who want us to build that particular technology for them, because sometimes it's a chicken egg problem. People have a rough idea what they want, and we know what the technologies can deliver. However, until they kind of see this particular technology in action, it can't really verify whether it was what they wanted in the first place. So having that iterative discussion where you build something, you show people this is what it's meant to do, and then you get a confirmation from the industry partner to actually ensure that's exactly what they wanted to achieve. It's actually critical. Maybe just along the line, sorry if I have digressed a little bit too much from it. The building a machine learning algorithm, there's a difference between building a machine learning algorithm versus contracting someone to actually building a website. Can I just say the difference is that building a website or doing an IT sort of consultancy, you know exactly what you're going to pay for, because if it didn't work and it didn't work. Now, getting someone to actually do a data science or machine learning algorithm, the algorithm will always output something, right? A bunch of numbers, a recognition results, and something. So it's sometimes you do not know whether these numbers are actually meaningful or useful. So therefore, it's always, so that's why it's important, I guess, to have scientific methods in order to actually verify the results as well. sorry if I have digressed a little bit.
Thank you. And in fact, it relates to the second last question I'm going to forward to you, noting the time, and thank you all for your questions coming in. So the interrelationship between human trial and error and artificial intelligence. Can AI be complemented by human trial and error? For example, for areas of farming where there isn't an extensive backlog of data collected, for example, on-farm management practices like pruning. The pruning interventions are not often recorded in the grape and wine industry.
Right.
Can human input be used to complement AI models, almost as a layer of input rather than a way of validating the system at the end of the AI process?
So I probably need to look at very specific examples of a human input because that is going to change the conversation altogether. But generally speaking, in terms of just the technical, talk about the algorithm itself, we very often have a constrained model. So the algorithm will do this, but you will have a constraints to be inputted. Whether these constraints come from a business, requirement, or whether it's come from a human, requirement, or human bill of labeling, or human specification, that can technically it is possible to combining, the two together.
Excellent. Thank you. So, ladies and gentlemen, I'm going to, if I may, and there are some related questions I haven't yet had time to do, I'm going to draw this to a close though. So for a start, firstly, Richard, thank you on behalf of our silent but very text-enabled audience for your presentation. Everyone, if you have any items you'd like to follow up with Richard, Richard's certainly available. Please reach out to him. A very modest Google search will find Richard very easily, given his global profile. We certainly encourage you to do that. If you feel there is anything that we within Food Agility CRC could do to improve your virtual research seminar experience, I would like to hear from you, Dave Lamb at foodagility.com. So please reach out because I see this, we're really keen to make this a regular part of our research communications activities. By all means, follow us on Twitter. We have a Food Agility handle, of course, like everybody and everything else nowadays, at Food Agility. If you yourself are excited about offering perhaps a seminar experience like Richard's offered us, I'd love to hear from you because you are part of our research community, our research capacity that's tackling the gnarly problems of today. And of course, if you'd like to engage with us as a researcher in meeting some of the challenges and opportunities of our agri-food sector, I'd also like to hear from you. So thank you all for your participation. Thank you, Richard, for your wonderful presentation and your answering of questions. Stay safe, stay connected, and stay sane. Keep your email eyes open for a notification or through Eventbrite of our recording on YouTube. And we look forward to seeing you at our next seminar, if not as a presenter, then as part of our wonderful audience. Thank you all.
All right, bye everyone. Bye Dave. Bye everyone.